This week in Environmental Science, we'll be taking a look at Chapter 17, Managing Our Waste. Here's our objectives for the chapter: to understand the types of waste that we generate, how to manage the waste, the scale of the waste dilemma, conventional waste disposal, ways to reduce waste, industrial solid waste management, and managing hazardous wastes. Our central case study for the chapter describes a mania for recycling on campus. In 2001, Ohio University and Miami University of Ohio competed in a 10-week recycling event. It was termed the first Recycle Mania. Miami University won. And as of today, 2014, Recycle Mania continues, and many colleges over the nation compete, over 461 to be exact, and many different awards are given for amounts and for types of wastes that are recycled. In 2014, Antioch University Seattle took top honors in Recycle Mania. It's the biggest of a growing number of campus competitions, all in the name of sustainability. The Campus Conservation Nationals is gaining momentum, and students on campuses across the country compete to see who can save the most water and the most energy. It helps campus sustainability to keep thriving. Students, faculty, staff, and administrators alike are doing the right thing, and competing in these competitions adds to the fun. A lot of good things can come from this. It encourages recycling. It cuts down on pollution from the mining of new resources and the manufacture of new goods. Each year, students in the event help to prevent the release of over 120,000 tons of carbon dioxide, which would be equal to the emissions output of over 25,000 cars, or the electricity use of 15,000 homes. By focusing the attention on waste issues, Recyclemania facilitates the expansion of campus waste reduction programs, and it gets a new generation of young people revved up for all the benefits of recycling. Waste refers to any unwanted material or substance that results from a human activity or process. Waste can degrade water quality and soil quality, air quality, and even human health. And it indicates inefficiency, so reducing waste can save money and resources. And for these reasons, waste management has become a vital pursuit. For management purposes, we can divide waste into several categories. One is municipal solid waste. These are non-liquid waste from homes, institutions, and small businesses. Industrial solid waste, number 2, is from the production of goods, mining, agriculture, petroleum extraction, and refining. And third, hazardous waste is the solid or liquid waste that's toxic and chemically reactive, flammable, and corrosive. Another type of waste is wastewater, and that's the water we use in households and businesses and industries, and we flush it down our pipes as well in the polluted runoff from streets and storm drains as well. There's 3 main components of waste management. Number 1, minimizing the amount of waste that we generate. 2, recovering discarded materials and finding ways to recycle them. And 3, disposing of waste effectively and safely. We have several ways to reduce the amount of material in the waste stream. That's the flow of waste as it moves from sources to its disposal destinations. Most U.S. municipal solid waste, or also called trash and garbage, consists of paper, yard debris, food scraps, and plastics. The latter two are the largest components. And most municipal solid waste comes from packaging and non-durable goods that are discarded after a short time of use. As we get more goods, we generate more waste. U.S. citizens generate about 7.1 pounds per person per day. And critics label the U.S. as the throwaway society, although U.S. waste decreased slightly from 2005 to 2012. Here's some diagrams showing the U.S. municipal solid waste stream. Developing nations produce waste as well. Consumption is greatly increasing in developing nations due to their rising standard of living and having more packaging and poor quality goods. Wealthy consumers discard items that can still be used, unfortunately. Poor people support themselves by selling items that they scavenge from dumps. Trash is piling up and littering the landscapes of countries from Mexico to Kenya to Indonesia. Plastics, which came into wide consumer use only after 1970, have accounted for the greatest relative increase in the waste stream during the last several decades. Wealthier nations can afford to invest more in waste collection and disposal, so they're often better able to manage their waste and to minimize impacts on the health and the environment. Recycling and composting are decreasing the pressure on landfills, which are filling up. In 2012 in the U.S., 35% of waste was recycled or composted. In modern sanitary landfills, waste is buried in the ground or piled up in mounds engineered to prevent waste from contaminating the environment and threatening public health. Most municipal landfills in the U.S. are regulated locally or by the states, but they must meet national standards set by the EPA under the Resource Conservation and Recovery Act, which was a major federal law enacted in 1976 and then amended in 1984. In a sanitary landfill, waste is partially decomposed by bacteria and compresses under its own weight to take up less space. Soil is layered along with the waste to speed decomposition, reduce odor, and lessen infestation by pests. Some infiltration of rainwater into the landfill is good because it encourages biodegradation and bacteria. Yet, too much is not good because the excess water can flow out, allowing contaminants to escape. To protect against environmental contamination, U.S. regulations require landfills be located away from wetlands and be away from earthquake-prone faults. The bottoms and sides of sanitary landfills must be lined with heavy-duty plastic and 60 to 120 centimeters of impermeable clay to prevent contaminants from seeping into aquifers. Sanitary landfills also have systems of pipes, ponds, and treatment facilities to collect and treat leachate. That's the liquid that results when substances from the trash dissolve in the water as rainwater percolates downward. Once a landfill is closed, it's capped with an engineered cover consisting of layers of plastic, gravel, and soil. And managers are required to maintain leachate collection systems for 30 years thereafter. Landfills have drawbacks. Despite improved technologies, liners can be punctured, and leachate collection systems won't always be kept up. And it takes decades for waste to decay. And then there's the thought called the not in my backyard syndrome, NIMBY, that residents don't want landfills in their areas. Wealthy, educated people have the political clout to prevent landfills from being sited in their own neighborhoods. And so, landfills are disproportionately sited in poor and minority communities. Landfills can be transformed after closure. In 1988, the U.S. had 8,000 landfills, but today there's fewer than 2,000 because they're large. Cities have converted closed landfills into public parks, stadiums, gardens, wetlands, and festival events. Incinerating trash reduces pressure on landfills. Incineration is a controlled process that burns garbage at very high temperatures. The metals are removed and the rest is burned in a furnace, and the remaining ash is toxic and must be disposed of in a hazardous waste landfill. Unfortunately, hazardous emissions are created and released when this happens. But scrubbers can chemically treat emissions to remove hazardous chemicals and neutralize acidic gases. Particulate matter called fly ash contains some of the worst dioxin and heavy metal pollutants in incinerator emissions. To physically remove these tiny particles, facilities may use a huge system of filters known as a bag house. In addition, burning garbage at especially high temperatures can destroy certain pollutants, like PCBs. But even with all these measures, however, we don't fully eliminate all toxic emissions. Incinerating waste reduces its weight by up to 75% and its volume by up to 90%. Incineration reduces the volume of waste, and today it serves to generate electricity as well. Most incinerators now are waste to energy, or WTE, facilities. They use the heat produced by waste combustion to create electricity. It boils water, which creates steam that drives electricity generation or that fuels heating systems. When burned, waste generates about 35% of the energy generated by burning coal. Combustion in WTE plants is not the only way to gain energy from waste. Deep inside landfills, bacteria decompose waste in an oxygen-deficient environment. This anaerobic decomposition produces landfill gas, a mix of gases roughly half of which is methane. Landfill gas can be collected, processed, and used in the same way as natural gas. Today, hundreds of landfills are collecting landfill gas and selling it for energy. Here's a diagram of a waste-to-energy incinerator, including some of the parts that we've just discussed, like the scrubber and the bag house. Reducing waste is our best option. Reducing the amount of material entering the waste stream avoids costs of disposal and recycling. It helps conserve resources, it minimizes pollution, and can save consumers and businesses money. Recall that preventing waste generation in this way is known as source reduction. Most waste consists of materials used to package goods. To reduce waste, use minimal or recyclable packaging. Buy unwrapped fruit and vegetables. Reduce the size or the weight of goods and the materials you use. And choose products that motivate producers to create longer lasting goods. These are some of the things that we can do. Some local governments are trying to reduce plastic bags. Grocery bags can take centuries to decompose because they're made of plastic. They choke and can entangle wildlife and cause much litter. 100 billion of them are discarded each year in the U.S. So many governments have banned non-biodegradable bags. And they tax on bags that gives financial incentives to use other bags. So then consumers are motivated to bring their own. Here's a chart of some actions we can all take to reduce the waste that we generate. From donating used items to charity, to selecting goods with less packaging, composting kitchen and yard waste, and supporting organizations that promote waste reduction, to name a few. Composting is the conversion of organic waste into mulch or humus through natural decomposition. We can place waste in compost piles, underground pits, or specially constructed containers. As waste is added, heat from microbial action builds in the interior and the decomposition proceeds. Banana peels and coffee grounds and grass clippings and leaves and other organic items can be converted into rich, high-quality compost through the actions of earthworms, bacteria, soil mites, sow bugs, and other detritivores and decomposers. Then the compost is then used to enrich our soils. On-campus composting is becoming popular, such as on Ball State campus in Indiana and in Ithaca College in New York. Municipal composting programs divert yard debris and increasingly food waste as well out of the waste stream. Recycling consists of 3 steps. Step 1 is the collection and processing of recyclable materials through curbside recycling or designated locations. Materials recovery facilities, or MRFs, are workers and machines that sort, clean, shred, and prepare the items. Step 2, using recyclables to produce new goods, like glass, metal, paper, plastic, and used recycled materials can be used to produce new things. And in step 3, consumers buy goods from recycled materials. There should be incentives for further recycling, and facilities can be built or expanded for this. Recycling has grown rapidly. 9,000 recycling programs serve 50% of Americans, and the U.S. recycling rates vary depending on product and state. Businesses see that they can save money when they do this, and entrepreneurs are motivated to start new businesses. So the U.S. recycles 26% of its waste stream. Recycling rates vary greatly depending on the product or the material, such as shown in this chart here. Many colleges have students that are getting involved in programs like Recycle Mania that we talked about earlier, or trash audits and landfill on the lawn. Louisiana State University recycled 68 tons of its refuse, and the University of North Carolina at Greensboro performed a trash audit to show how many recyclable items are thrown away needlessly. It can be an eye-opener when people do this. Recycling has grown for many reasons, such as municipalities that just want to reduce waste, and the public takes satisfaction in recycling. It may not be profitable, however. To collect, sort, and process the materials is expensive, and the more material that's recycled, the lower the price. Transportation costs to recycling facilities could be high as well. But market forces do not take into account the health and the environmental effects of not recycling. So recycling offers enormous savings in energy and materials. Now we come to the science behind the story section of our chapter on tracking trash. Where does your trash go once you throw it away? What happens to your recycling? How far might it travel? And how much energy is needed to get rid of it? Researchers from the Sensible City Lab at Massachusetts Institute of Technology, or MIT, place tracking devices on various kinds of trash in New York City and Seattle. Then the movements of the items were tracked. Hazardous waste items and electronic waste items tended to travel furthest because they were sent to special facilities for handling. That raises a question of whether special handling is actually worthwhile, given the impacts of the extra gasoline use and the greenhouse gas emissions required to transport these items. These data will be used to improve the ways that we handle wastes. We can recycle materials from landfills. Businesses are weighing the benefits of salvaging materials in landfills that could be recycled, like metals, organic waste for compost, waste that could be incinerated, and harvesting methane from open dumps in Asia and Africa. But costs and regulatory requirements have made investing in landfill mining risky, and rising prices and better technologies will hopefully change this. Waste managers offer consumers economic incentives to reduce the waste stream. In pay-as-you-throw garbage collection programs, municipalities charge residents for home trash pickup according to the amount of trash they put out. The less waste one generates, the less one has to pay. Over 7,000 such programs operate in the U.S. today, serving more than 1 out of every 4 communities. Bottle bills are another approach, hinging on financial incentives. In the 10 U.S. states and 23 nations that have these laws, consumers pay a deposit on bottles or cans upon purchase, often about 5 cents per container, and then receive a refund when they return them to the stores after use. Where these laws have been enacted, they've proven effective and popular. U.S. states with bottle bills report that their beverage container litter has decreased by 69 to 84%. Their total litter has decreased by 30 to 65%, and their per capita container recycling rates have risen 2.6-fold. Beverage container recycling rates for states with bottle bills are 2.5 times higher than for the states without them. As of 2014, bottle bill advocates in 13 states were seeking to establish, expand, and update their programs. In the U.S., industrial solid waste is defined as solid waste that's considered neither municipal solid waste nor hazardous waste under the Resource Conservation and Recovery Act. This includes waste from factories, mining activities, agriculture, petroleum extraction, and more. Each year, the U.S. industrial facilities generate about 7.6 billion tons of waste, according to the EPA, about 97% of which is wastewater. Thus, very roughly 230 million or so tons of solid waste are generated by 60,000 facilities each year, an amount approaching that of municipal solid waste. The federal government regulates municipal solid waste. States and local governments regulate industrial solid waste with federal guidance, and state and local rules are less strict than the federal rules. Most methods and strategies of waste disposal, reduction, and recycling are similar to those for municipal solid waste. Industries may not be required to have permits or install liners or leachate collection systems, or even to monitor groundwater for contamination, and it may be cheaper to generate waste than to avoid it. Industries are awarded for economic, not physical efficiency. Once government or the market makes it efficient, businesses then gain incentives to reduce their waste. But industrial ecology seeks to make industry more sustainable. Industrial ecology involves redesigning industrial systems to reduce resource inputs while maximizing physical and economic efficiency. Based on principle that industrial systems should function like ecological systems with little waste. They examine the entire life cycle of a product, from its origins and raw materials through its manufacturing to its use, and finally to its disposal. And they look for ways to make the process more efficient. And that strategy is called life cycle analysis. Industrial ecology examines how waste products can also be used as raw materials. It eliminates harmful products and materials and creates durable, recyclable, and reusable products. Businesses are saving money while reducing waste when they adopt industrial ecology. Attentive businesses are taking advantage of the insights of industrial ecology to save money while reducing waste. For example, few businesses have taken industrial ecology to heart as much as the carpet tile company called Interface, which founder Ray Anderson set on the road to sustainability years ago. Interface asked customers to return used tiles for recycling and for reuse as backing for new carpet. It modified its tile design and production methods to reduce waste. It adapted its boilers to use landfill gas for energy. Through such steps, Anderson's company cut waste generation by 80%, fossil fuel use by 45%, and water use by 70%, all while saving $30 million per year, holding prices steady for customers, and raising profits by 49%. Swiss Zero Emissions Research and Initiatives, or ZERI, Foundation sponsors dozens of innovative projects worldwide that attempt to create goods and services without generating waste. One example involves the breweries in Canada, Sweden, Japan, and Namibia. Hazardous wastes are diverse in their chemical composition and can be liquid, solid, or gas. By the EPA definition, hazardous waste is a waste that's one of the following: ignitable, meaning it's likely to catch fire; corrosive, it can corrode metals in storage tanks or equipment, for example, strong acids and bases. It's reactive, meaning it's chemically unstable and readily able to react with other compounds, often explosively. Examples could be ammonia reacting with bleach. And then toxic, which is harmful to human health when inhaled, ingested, or touched. For example, pesticides and heavy metals. Industry produces the largest amount of hazardous waste, but waste generation and disposal are highly regulated here. Households are the largest source of unregulated hazardous waste, including paint, batteries, solvents, cleaners, and pesticides. Many hazardous substances become less hazardous over time, but others can be especially persistent, like radioactive waste, organic compounds, and heavy metals. U.S. citizens generate 1.6 million tons of household hazardous waste annually, and the average home contains close to 100 pounds of it in their sheds, basements, closets, and garages. Synthetic organic compounds resist bacterial, fungal, and insect activity, like plastic and tires, pesticides, solvents, and wood preservatives. It keeps buildings from decaying and kills pests and keeps stored goods intact. But their resistance to decay makes them persistent pollutants, stick around a long time. They're toxic because they're readily absorbed through the skin and can act as mutagens, carcinogens, teratogens, or endocrine disruptors. Lead, chromium, mercury, arsenic, cadmium, tin, and copper are used widely in industry for wiring and electronics, fabrication, pigments, and dyes, and then enter the environment when they're disposed of improperly. And these heavy metals that are fat soluble and break down slowly can bioaccumulate and biomagnify, meaning they're going to infect or affect our higher level trophic feeders. E-waste is growing. Electronic waste is called e-waste. It involves electronic devices like computers, printers, and cell phones, TVs, and MP3 players. And Americans discard 300 million of these devices per year. And in fact, 3/4 of them would actually still work. They're put into the landfills, but should be treated as hazardous waste. Valuable trace minerals could have been recovered in them. For instance, the 2010 Olympic medals were made from e-waste. And electronic waste is increasing, as shown by this chart. Several steps precede the disposal of hazardous waste. Communities designate sites, collection days, and facilities to gather household hazardous waste, and then the waste is transported for treatment and disposal, and it's done properly. Under the Resource Conservation and Recovery Act, the RCRA, the EPA sets standards, but the states manage hazardous waste. Large generators of hazardous waste must obtain permits, and materials must be tracked from the cradle to the grave, and it's intended to prevent the illegal dumping of them. Hazardous waste disposal is costly, which then often results in their illegal dumping. Industrial nations illegally dump in developing nations. The Basel Convention, an international treaty, should prevent dumping, but it still happens. High costs also encourage companies to invest in reducing their hazardous waste. Many biologically hazardous materials can be broken down by incineration at high temperatures. Others can be treated by exposure to bacteria that break down harmful components and synthesize them into new compounds. We have developed 3 primary means of hazardous waste disposal: landfills, surface impoundments, and injection wells. These do nothing to lessen the hazards of the substances, but they keep the waste isolated from people, wildlife, and ecosystems. Design and construction standards for hazardous waste landfills are stricter than those for ordinary sanitary landfills. Hazardous waste landfills must have several impervious liners and leachate removal systems and must be located far from aquifers. Liquid hazardous waste, or waste in dissolved form, may be stored in surface impoundments. Those are shallow depressions lined with plastic and an impervious material like clay. The liquid or slurry is placed in the pond and water is allowed to evaporate, leaving the residue of solid hazardous waste on the bottom. This process is repeated and eventually the dry residue is removed and transported elsewhere for permanent disposal. Impoundments are not ideal. The underlying layer could crack and could leak waste. Some of the material may evaporate or blow into the surrounding areas, and rainstorms may cause waste to overflow and contaminate nearby areas. For these reasons, surface impoundments are usually only used for temporary storage. The third method is intended for long-term disposal. It's called deep well injection. It's where a well is drilled deep beneath the water table into porous rock, and the wastes are injected into it. The process aims to keep hazardous waste deep underground, isolated from groundwater and human contact. However, the wells can corrode and leak the waste into the soil and can contaminate aquifers. Roughly 9 billion gallons of hazardous waste are placed in U.S. injection wells each year. Many thousands of former military and industrial sites remain contaminated with hazardous waste in the United States and virtually every other nation on Earth. For most nations dealing with these messes, it's simply too difficult and time-consuming and expensive. But in 1980, however, the U.S. Congress passed the Comprehensive Environmental Response, Compensation, and Liability Act, also called the CERCLA. This law established a federal program to clean up the U.S. sites polluted with hazardous waste. The EPA administers this cleanup program called the Superfund. Under EPA, experts identify polluted sites and take action to protect groundwater and clean up the pollution. Later laws also charged the EPA with cleaning up brownfields, lands whose reuse or development is complicated by the presence of hazardous materials. Two well-publicized events spurred creation of the Superfund legislation. In Love Canal, a neighborhood in Niagara Falls, New York, families were evacuated in 1978 to 1980 after toxic chemicals buried by a company in the city in past decades rose to the surface, contaminating homes and an elementary school. In Missouri, Times Beach, an entire town was evacuated and its buildings were demolished after being contaminated in the 1970s by dioxins from waste oil sprayed on its roads. Once a Superfund site is identified, EPA scientists note how close it is to humans, whether wastes are currently confined or likely to spread, and whether the site threatens drinking water. Harmful sites are then put on the national priority list and then ranked by their level of risk to human health, and then cleanup occurs as funds are available. The EPA must hold public hearings to inform area residents of its findings and to receive feedback. CERCLA operates under the polluter pays principle, charging polluting parties for cleanup. However, the responsible parties often can't be found. A trust fund was established by federal tax on the petroleum and chemical industries. The fund is bankrupt and the Congress has not restored it, unfortunately, and now taxpayers pay all the costs of the cleanup. Fewer cleanups are being completed. Still, 1,326 sites remain and only 375 have been cleaned up, and each cleanup costs $25 million and takes about 15 years. In conclusion, we've made great strides in addressing our waste problems. Modern methods of waste management are far safer for people and gentler on the environment than past practices of open dumping and open burning. Recycling and composting efforts are advancing steadily, and Americans now divert 1/3 of all solid waste away from disposal. The continuing growth of recycling, driven by market sources, public policy, and consumer behavior, shows potential to further alleviate our waste problems. Despite these advances, our prodigious consumption habits are creating as much waste as ever. Our waste management efforts are marked by a number of challenges, including the cleanup of Superfund sites, safe disposal of hazardous and radioactive waste, and local opposition to disposal sites. These dilemmas make clear that the best solution is to decrease our generation of waste by finding ways to reduce, reuse, and efficiently recycle the materials and goods that we use.